All right, so today is the last only meeting for this week. For my classes at Rowan, I'm going to be recording an introduction to hypothesis testing, and I can give you guys a copy of that also, allow you guys to look at it also. It's basically the same material. I'm not going to go into formulas or anything like that, just the general theory behind it and how the symbols behind it and how it works in general. All right, so that might be useful for both of you to see that. So I'll post it tomorrow night. Planning to do it tomorrow. It won't be too long, maybe about an hour, but it'll give you an idea of what we'll be dealing with next, the next topic. All right, chapter 10 topic. All right. All right, so tonight I think we're going to be going over sample problems from chapter 9. Let me tell you which ones they are. So let me share the screen. I don't look at the solutions, but I don't want you to try these on your own. But 9.83, 9.84, 9.85, 9.87, 9.91, 9.100, and also 104. Those, we're going to be looking at those. I guess there's 6 of them. Page 305, 306. Start with 83. We'll go to 84, 85, and 87. Let's start with those. All right. So let me stop sharing so you can see the solutions. All right. And this is at the end of page 9. So let's share the screen with the textbook. And we'll go right to the end chapter. All right. Exactly what I'm looking at here. All right, end of chapter review. So, yeah, here they are. I'm going to start with 9.83. In your book, it's page 305. All right, so take a look at, let's look at what it says, and then I'll give you a few minutes to try this. There's a torque wrench used in the final assembly of cylinder heads as a process standard deviation of 5 pound-feet. The engineers have specified that a process average of 135 pound-feet is desirable. For a simple random sample of 30 nuts that the machine has recently tightened, the sample mean is 137 pound-feet. Construct and interpret the 95% confidence interval for the current process mean. Discuss the possibility that the machine may be in need of adjustment to correct the process mean. All right, so they do give you in this particular problem, they give you a process standard deviation. That's not from a sample, is it? Correct? That's your population standard deviation. All right, this is you're estimating a population mean in this case here, right? Mm-hmm. Right. You're supposed to construct a 95% confidence interval for the current process mean, the population mean. All right. They're anticipating a process average of 135. Right? They got 137 as for the sample mean. So go ahead and use the formulas that we talked about last time. and construct a 95% confidence interval. Right? And the first step, of course, is to calculate your margin of error. Go ahead and do that, and then add and subtract that from the sample mean, and you should get your 2 endpoints. And you can round the endpoints to 3 decimal places. All right, guys, are you done?
Yes.
All right. So what did you get for your interval? Either one of you can yell out.
135.211 to 138.789.
Correct. Correct. And Han, did you get the same? Did you get the same? No? All right, so let's take a look.
No.
That's all right. Let's take a look at the solution. All right, so the population standard deviation is 5, and 30 is your sample size, and your mean is 137. This is the general formula for a confidence interval. Sample mean plus or minus the margin of error. The margin of error is the critical value times the standard error. The 95% confidence interval, since we know population mean, excuse me, the population standard deviation, we're going to use a Z critical value. And hopefully you already know this without looking it up, right? That 1.96 is the Z critical value for a 95% confidence interval when we use a Z. So 1.96 times this ratio, 5, divided by the square root of 30, is our margin of error. It's approximately 1.789. And then you add and subtract it from the 137, which is the sample mean, and you get those two endpoints for your estimated population mean. This is one way of writing it, by the way. You could say the population mean mu is somewhere in between these two values here with 95% confidence. Right? And they're asking whether there should be some adjustment to the process, and the answer is yes. You should consider it because what they're saying is the true mean is 135 and it's outside the interval. All right. So if they're getting, if there's a, this is 90, they're 95% confident the true mean is in between these two values, and they're thinking it's 135, it's out, which is less than the lower end, then it's probably a good idea to consider adjusting the process. All right. In other words, in the language, we're assuming 135 is true, but since we're getting this interval here, 135 is outside the interval, we might consider that this 135 is not true. Or the other way around, if we consider it the other way around, if we do think 135 is true, then the process that created this this sample mean is not correct. It needs to be adjusted. All right. So there's two ways of looking at it. All right. Let's now look at 9.84, which I will read. Let's go back to the book. There are approximately 113 million television households in the United States. Of course, this was way back when, right? Many more probably now. A rating service would like to know within 5 percentage points and with 95% confidence, the percentage of these households who tune in to the first episode of a network miniseries. How many television households must be included in the sample? Another way of saying this is, what is the minimum sample that you need to have in your study, right? Why? To meet these requirements. Level of confidence, 95%, and it says within 5 percentage points. What does within mean? Another way of saying within. In the context of what we've been talking about. When we say within 5 percentage points, what does this 5 percentage points represent?
Proportions of the population?
Well, it is a proportion, but what does it represent in the context of confidence intervals? They say within 5%. What do they mean?
Like the sample size won't be bigger than 5% of the population?
No. No, that's not. It's not doesn't have anything to do with the size of the sample. Well, it does. It does, but in an indirect way.
Oh, you mean so the margin of error will be
Margin of error. That's it. It is the margin of error. And you see within, it means either less or greater than that amount. It's the margin of error.
okay.
What? Han, do you understand that? Get that idea? What I'm saying is I'm within 5 feet of somebody. I'm either let's assume there's a line, right? We're standing on a line and I'm within 5 feet of you. I'm either to the left of you within 5 feet or I'm to the right of you within 5 feet. Isn't that what we mean by margin of error? If you are the mean and I'm within 5 feet of you on the left or right, 5 feet is the margin of error. Does that make sense? You're either subtracting 5 feet to the left or you're adding 5 feet to the right. I'm either to the left 5 feet less than where you are or to the right 5 feet more than where you are? Picture that in your mind.
5 feet, 5 feet is a number, but
Well, I'm just,
5%.
yeah, I get it. But that's, I was just, it's an analogy.
Okay.
Analogy. I'm not trying to say exactly like this. It's an analogy. Analogy means something similar. So when I say within
Yeah.
5 feet, I'm just trying to give you a visual idea that when these problems say within, it's referring to the margin of error. That's all. So in this case, Han, what we're estimating is a proportion or a percentage, if you look at it as a percentage also. So when they say within 5 percentage points, that is the unit of measurement as opposed to feet. See what I'm saying? If we're measuring a proportion, it's either in decimal points or percentage points. That's the unit of measurement. Han, you're frozen. I can't see. Han is frozen. She seems to be frozen forever. Maybe she'll unfreeze in a minute. Anyway, go ahead, Steve and Han, if you can hear me. Maybe you can't. Go ahead with 8.80, problem 84. There you are. You completely froze, Han. Han, you'll need to unmute yourself.
Ask you.
Huh? Are you okay? Something's wrong with her video. She's completely frozen.
I can't see any of.
All
Can't
right.
see you. Like I can't see your this.
Yeah, Steve, you
Is
can
it
see
my
me?
problem?
Steve,
It looks like it's your problem. I can't see your feed. I can see Professor Barish's though.
yeah. So Han, you need to maybe exit out and maybe come back in. Try that. All right, Steve, go ahead and continue working on it, and Han will have to go ahead and do that. Oh, it seems like Han's coming back in. There you are. Can you see me okay now, Han? Han, can you see me?
Yes. Yes.
See the screen okay?
Yes.
All right, good. So have you tried 9.84 yet?
No.
So why don't you try it? Or you can just
Okay.
wait. Or Steve, are you done? Steve, are you done?
No, not yet.
Not yet. All right, so Han, why don't you try it? And
Okay. Okay.
give you 5 minutes, maybe 3, 4 minutes, something like that. Now, we did not cover this last time, this mini topic here. So if you're struggling with it, that's understandable. So should we stop and take a look at the solution? Would that be useful?
Yeah. Yeah, I got a really I got an N that is extremely small. So
You mean like decimal small?
yeah, let's.
Okay.
Yes, yes. The answer that I got is really small.
All right. Okay. So let's take a look at the solution. Now, the solution will, I think the best way of teaching this topic is just doing it in because the topic is regarding what researchers would do before they actually do a study. They have to determine if they're going to do sampling, they have to determine how big of a sample do they need, right? They don't just guess at it. They need to estimate their minimum sample. And what they want when they do a confidence interval is they want to meet certain requirements. They want a confidence level. Now, it could be in a particular field of research that everybody says 95% confidence interval. Everybody uses it, okay? So you wouldn't be any different than anybody else in your field of study, right? Maybe it's 99%. Whatever it might be, you go with that. The other thing is you want to determine up front your margin of error. How wide do you want your interval to be? Remember, the interval is going to be twice the margin of error, the length of the interval, twice the margin of error, because you're subtracting from one end and you're adding on the other end. So you're literally doubling the margin of error when you subtract the two endpoints. So most people want as narrow a margin of error as they can have within reason, given the level of confidence. And they want to figure out, all right, how many people or things do I need to sample? At a minimum. You can sample more if you want, at a minimum. So the way to figure this out is if you're estimating a population proportion, your confidence interval, you'll want to use this formula here. ME means, it's my symbol for margin of error, all right? You can put E, I think the book uses small e or something. Whatever you want to use, that's fine. I like ME because it means margin of error. So the book says in 9.84, I want the margin of error to be, it doesn't even say margin of error. I want my estimate to be within 5 percentage points, right? Well, this is a proportion. So when they say 5 percentage points, they mean 0.05. You convert that to a decimal. So that's why I have ME is equal to 0.05, my margin of error. Now, it's a 95% confidence interval. I know Z is 1.96. The thing that's not given to me, which I will need, is an estimate for the sample proportion or an estimate of the population proportion, whatever. We need an estimate of it because the formula for the margin of error, which is where we're going to get n from, you remember, if this is the formula right here for the margin of error, it's the critical value Z times the standard error, which is the square root of p hat times 1 minus p hat divided by n. Well, they don't give you an estimate for p hat in the problem. If you read through it, there's nothing about that. So the question is, what do you use? And the answer is, you're going to use the most conservative estimate for p hat, which is 0.5. If p hat is 0.5, 1 minus p hat is also 0.5. And when you multiply those two numbers, 0.5 times 0.5, you're going to get 0.25, right? See that in the numerator of the margin of error formula. It's p hat times 1 minus p hat. Now, it just happens to be that that is the largest number. That's the product of p hat and 1 minus p hat, period. When p hat is 0.5 and 1 minus p hat is 0.5, 0.25, that product of those two numbers is the largest that you can possibly get for any p hat or 1 minus p hat combination. So what we're basically doing is we're being conservative, right? We're going to end up with a wider interval than we would necessarily have if we had an estimate for p hat. But it's okay. We'll use 0.5 for p hat. So if there's nothing in the problem that refers to an estimated proportion, then use 0.5 for p hat. That's the general rule, all right? Which is what I used here. Now, notice what I did here. I took the formula for my margin of error, and then what I literally did is I squared both sides because the n is inside the square root. So to get rid of the square root, I have to square both sides. And when you square both sides and rearrange the terms, you end up with this formula solving for n. You have your critical value divided by the margin of error, the quantity squared, times p hat times 1 minus p hat. Okay? So square both sides and then solve for n, and you get this formula here. It's in the book. So I just plug everything in. I'm plugging in 1.96 for the critical value because it's a 95% confidence interval. ME, the margin of error is 0.05. That goes into the denominator. And you have to remember, Steve, maybe you forgot to do this. You have to square that. And then when you multiply 0.5 times 0.5, obviously you get 0.25. And you multiply all these things together, you get 384.16. And what this is what you always do. Always do this. If you get a decimal, no matter how small the decimal, you always round up to the next whole number. So unless you get an exact whole number answer, you always round up to the next whole number, which makes sense, right? Because you're counting the number of people or things that you're going to be sampling, which are whole numbers, people. So you always round up next whole number, and it's 385. All right. All right. Any questions about that?
No.
I would have been surprised if you got that correct. I wanted to allow you to give it a shot, but the p hat, I wouldn't have expected you to know that ahead of time. Now, the next problem is the same problem as 9.84. If you read through it, though, 9.85, it says, suppose a small-scale preliminary survey has indicated that no more than 20% of television households will tune into the first episode of the miniseries. So now we have our estimate for p hat, 0.2. All right, 20% of 0.2. So now what we're going to do is we're going to take that same formula. What's inside the ratio inside the square term here is going to stay the same. You're just replacing p hat with 0.2, which means 1 minus p hat is 0.8. And when you multiply all of that together, you get 245.86, and you round it up to 246 as your minimum sample.
Mm-hmm.
And that's how you do this. It's, you know, once you know how to do it, it's pretty straightforward. You just have to know what to look for. And you have to, of course, this is very important. You have to recognize it as a proportion question, right? You have to recognize it as a proportion question as opposed to something that we're measuring. Yeah. All right. Any questions about that? So 9.84, 9.85 go together, but they give you both types of minimum sample size problems for proportion or estimating proportion. Either you know p-hat or you don't know it. And both of those are able to answer that question. All right. That's all there is to it. I mean, I can give you more examples, but it's just basically the same thing. You know, you just need to know how to do it once. And again, open book, right? You don't have to memorize anything. You just plug in the numbers and you have your answer. You don't really need a spreadsheet for this. The only thing you might want to use a spreadsheet for, obviously, is to get the critical value. Now, you may ask the following question. Remember last time I introduced you guys to the T distribution, right?
Right.
And remember the T distribution, the only parameter that defines the T distribution is the degrees of freedom, which is the sample size minus 1. So your question might be, well, why didn't I use a Z critical value in estimating or coming up with my minimum sample? Well, there's a real problem doing that, isn't there? Because if the critical value depends on the sample size and you're trying to determine the sample size, you have like a circular problem there, right? You can't solve it. Yeah. You basically have to have some computer to figure that one out. So that's why you need an estimate. Well, in this case here, you don't need, to be honest with you, that's only in the case of when you want to find a minimum sample size for a mean, for population mean. Not in this case. The T critical value is never used for proportions. All right. We'll get to that in a minute about the T critical value, but you don't want to use a T critical. This my point is, you never want to use a T critical value when you're trying to figure out your minimum sample size. It's never going to work. All right. So let's look at 87. Let me actually go out of here. I don't want you to look at this. So we're going to go to problem 87. Look. Now, 87 actually has, and I didn't give this to you. I probably should have, but remember, we're using Excel right now, and I guess this would have been okay for Excel. I want you to take a minute, open up Excel, and I want you to, in one column, anywhere in the spreadsheet, I want you to enter all of these numbers here. I think there are 30 of them, right? There's 10 in a row. There's 30 numbers here. Just be careful. Make sure you enter them all correctly. Doesn't matter which order you enter them in. Just enter all 30 numbers that are shown here. And then what we're going to do, according to this problem here, is we're going to construct both a 90% and a 95% confidence interval for a population mean. All right. Now, these are household incomes in thousands of dollars. So, for example, 58.1 would be $58,100, be the annual income. All right. So we'll use the numbers that we have here. We'll construct the interval in thousands of dollars. So, if the left end is like 30.2, we'll just say 30.2. We know it's in thousands of dollars. All right. So enter all this into your whatever you're using, your Excel spreadsheet, or if you had a calculator, use a calculator. And then obviously what you need is the following. First of all, is there anything in this problem here that tells you a population standard deviation?
Population, no.
No. They're giving you a sample and they're asking you to construct confidence intervals. So this is a perfect example in which you would not use population standard deviation. You have to use the sample standard deviation. So you need to actually calculate that also. Make sure that you get the sample standard deviation, not the population one. when you use your functions on Excel. So you need your sample mean, your sample standard deviation, and then you may want, now for 95%, you don't know, this is very important, you do not know the t critical value. It's going to be different than the z critical value, because in this case, because we're using the sample standard deviation, we must use the t critical value. It is a common mistake with people who are beginning students with statistics, that they make the mistake of using a z critical value in this case. Whenever we replace the population standard deviation, which is unknown, with a sample standard deviation, we must use a t critical value for a t critical value. So we're going to use an inverse t, come up with that critical value in both intervals, okay? Then you're going to multiply that t times s divided by the square root of n, which is the standard error, and that'll be your margin of error. And then you add and subtract that to your sample mean, which will be the same number in whatever confidence interval we use, right? The confidence interval will still have the same mean and same sample standard deviation, the same sample size. The only thing that's going to change is your critical value. Critical value is going to change, right? So go ahead and do that. Work on that. I'll give you like 7 or 8 minutes. Let's say 8 minutes. I'm just going to take a little break, and I'll let you guys work on that. I'll be back in about 5 minutes. So work on that and see if you can come up with both of those intervals. Guys still working on it?
Yes.
I'll give you about 2 more minutes and then I'll show you the solution. Have you completed any of the intervals yet or just still working on the first one?
I'm still setting it up, but I'll have it soon.
All right. I don't want to keep you guys too late. You're almost there, both of you?
I got one of the ranges, but not the second one.
All right. What did you get for the first one, Steve?
For 95%, what I got was 44.343 to 50.524.
For the 95% one.
Yes.
Okay. Did you check in the back of the book at all? Because the back of the book has solutions for this one. Did you double check your?
Yeah, I did check, and it's not right, but it's not too far. So I'm wondering if it's just like a rounding error that I made.
Okay. All right. So let's go to the and the second one. Similar thing going on. Let's just I'll stop this and let's look at the solutions. And you can obviously do this second one on your own also. I just want to make sure we get through all the problems tonight. So here's 9087. All right. So for the 90% one, let's do the 90% one also. Let's do that for one first. Han, did you get any of them or did you still working on it? You were still working on it?
I forgot the formula for standard derivation.
You don't need a formula. Use Excel spreadsheet to use it. Maybe we should go.
Oh,
You forgot how to use Excel to find the standard deviation? Is that what you're saying?
Yes,
All right.
yes, yes.
All right, we'll just stop for a second here. Let's go into Excel here. Hold on a minute. Sorry. Let me just pull up Excel. Just do a quick, I'm just going to put some numbers in here. 2, 30, 5, 6, 8, 55, 75, 74, 100. All right, something like that. All right, so we have how many numbers here? We have 4 through 12. That's 9. One more we'll put in 152. There's the 10 numbers here. And to find the mean, obviously, to find the mean, we're going to say equal to average, right? Average. So average will do for the and then we'll just scroll down and we get our mean, right? There's our mean. So actually, I'm going to move it over here. All right, so I'm going to type in mean here. Standard deviation. And we want it for a sample. So just start, just put an equal sign and just start. Just start typing in standard. ST, oops, no A there, ST. And look, you immediately see a list. I just started typing. You don't need to remember anything. Excel is like this, where you could just start typing letters and then after the equal sign, and then you get this list. And STDEV.S is the sample standard deviation. STDEV.P is your population standard deviation. So choose the one that says S, and then just do the numbers again, like that. All right. And there's your sample standard deviation. Okay, that's it. And remember, the only time you're going to be needing to find a standard deviation from a data set is probably because it's a sample. So most likely you're going to use that particular function, right? And the function, once again, if you look at it, is STDEV.S. That's the sample standard deviation. All right. Forget about what I have here. These are obviously not the right numbers, but you get the idea now how to do it?
Yeah.
Yeah. Okay, good. All right. So let's stop and go back to the solutions. Now, I got a mean for this problem of 47.4333. There's a whole bunch of threes after. I just rounded it to 4 decimal places. And the sample standard deviation was 8.1374 when I rounded it to 4 decimal places. That's my sample standard deviation. Steve, did you get both of those correct? And Han, did you
Yes,
get?
I did. So I was copying my digits, for even more digits past the decimal than that.
Well, yeah, you can. If you were using a calculator, you would just store the number.
Oh, you know what? No, I see where I went wrong. I put in the square root of 29, not square root of 30. That's my mistake. Yeah.
Yeah, and that's it's the square root of n. So
Right,
yeah, you
right.
have to be very careful.
Yeah.
Knowing that the t critical value is based on n-1 degrees of freedom.
Right, right.
But this denominator is always the square root of the sample size, not the square root of the degrees of freedom. So yeah,
that's where I went wrong. Yeah.
Yeah. So that's it. Everything else looks good, right? The critical value you got correctly. Remember, you're going to use T inverse, right? T inverse, whatever it is in Excel. Han, did you know how to find a critical value in Excel?
Yes.
All right. So make sure you use 29 in this case as your degrees of freedom, not 30. 30 is your sample size. It's n-1, so it'd be 30 minus 129 is your degrees of freedom. And you should get 1.6991 if you round it to 4 decimal places for your critical value. You multiply that times your sample standard deviation, 8.1374, divided by the square root of 30, square root of sample size, and you should get your margin of error is 2.5244 approximately. And then that's what you add and subtract from the sample mean of 47.4333. And you end up with these two endpoints for your 90% confidence interval. Now, for the margin of error for a 95% confidence interval, the only thing that changes in this entire formula for the margin of error is the critical value. The standard error is the same, no different there. Critical value for 95% with 29 degrees of freedom for the T critical value is 2.0452. That's right. And you multiply that times the standard error. You get 3.0385 is your margin of error. And you add and subtract it, you get these endpoints, which matches the book's answer. The book might have rounded at these two decimal places, but using 4 decimal places, this should be approximately correct. I did some rounding here, right? You don't have to do the rounding. You don't have to do it at all on an Excel spreadsheet, right? There's no need to round. Whatever comes up, right? It's gonna be the full value on your whatever cell you're using for these quantities, and you just refer to those cells when you do your formulas, and you should get an exact answer, right? You should get something that without much rounding error. All right. So the key to doing this problem was a couple things. Number one, recognizing it as a mean, estimating a mean for the confidence interval. Number two, there is no population standard deviation, so you have to use the sample standard deviation instead, which means you have to use a T critical value. And that's it, right? That's all you needed to know to do this. Right. No questions? You're good with this now?
I'm good.
All right. And Han, you're okay?
For the ME, the
Margin of error.
1.6991, that part. Yes, I think you said we should divide 29.
No, you're not dividing anything with the critical value. You're using 29 degrees of freedom because the sample size is 30. Sample size is 30.
Mm-hmm.
Yeah. This here has nothing to do with, this number here has nothing to do with degrees of freedom. This, only the T critical value deals with degrees of freedom. There's no division here, Juan. You're not dividing anything. You're looking it up.
Okay.
Right? Yeah, that's all you're doing. You're figuring out what the critical value is based on what? 90% confidence, level of confidence, which means your area to the left is going to be 95%, 0.95, right? So when you find your T critical value, it's going to ask you for a probability or area. You're going to put 0.95 because it's the middle of the area plus the left tail. Left tail is going to be 5% in this case, right? Okay, because it's 10% left, half on the left, half on the right. Half of 10 is 5, so 5% on the left, 5% on the right. Middle, 90%. So the area to the left of the critical value is going to be the middle, 90% plus the left tail of 5%. 0.95 is going to be your area to the left. And your degrees of freedom is 29 because it's 30 minus 1.
Okay, gotcha.
That's the only reason you're using 29 for the critical value. The standard error is the standard error.
Okay.
You always divide it with, when you're estimating a mean, you always divide by the square root of sample size, period. No, you're not subtracting anything here. All right. So you're not dividing anything here, and you're not subtracting anything here. All right. Okay. Don't confuse those two things. The standard error is always dividing by the square root of sample size when we're estimating a mean. Always. We had, if this problem was a Z critical value, and we still use the square root of the sample size in your denominator here. All right. Yes. It's in that case, it would be sigma divided by the square root of n. But the denominator is always the square root of sample size in the standard error formula, period.
Okay.
All right, has nothing to do with degrees of freedom. All right, let's look at the problem 91, which is starts on page 305, goes into page 306. Let's take a look at that one. A research firm wants to be 90% confident that a population percentage has been estimated to within 3 percentage points. All right, immediately you know this is a proportion problem. The research manager calculates a necessary sample size with 0.5 as his estimate of the population proportion. Or they're even giving you that in this problem. All right. A new business school graduate who's just joined the firm questions the research manager further, and they agree that the population proportion is no more than 0.3. All right. If each interview, which means each person who's interviewed from the sample, costs $10 each, how much money has the new graduate just saved the company? All right. So what are they asking? What are they trying to figure out here? Remember, if you don't have a population or a estimate of the population proportion, right? Don't have an estimate of it, use 0.5 for proportions, correct? So that's what this research firm the research manager was planning to do. So here comes this new business school graduate, this, overconfident business school graduate, and says, I know better. You've been working here for 30 years, but I know better. And I think that it's 0.3 to the estimate. So what you need to do in this problem is calculate it both ways. Calculate the minimum sample size both ways, and and obviously the business school graduate will have a smaller minimum sample size, and just take the difference between those two sample sizes, multiply it by $10 per sample, and that's how much this graduate saved the firm. All right, makes sense? So go ahead and do that and let me
Yes.
know. Yeah, good. It should only take you about 2 to 3 minutes to do this problem. Go ahead and do it and come up with that number for me. All right, so Steve, you have an answer, I guess, right? Han, you have an answer too? All right, Han, what did you come up with?
1,200.
Great. And Steve, you agree? Good.
I agree.
Good, good. So just for the, for Rose to see the solution, which I will post, of course, let her take a look at it. So next one here it is. We have our 90% confidence interval that we want. Originally, the research manager is going to pick 0.5 as the estimated proportion. Margin of error, it says within 3% percentage points, is 0.03 is the margin of error. Using this as our formula for our minimum sample, and we have a 90%, you would have probably determined that your critical value is 1.6545, or I actually just use 4 digits here, 1.6449. Margin of error is 0.03. I'm going to square that ratio and then multiply it by 0.05 squared. And I get 751.582 and round that up to the next whole number, 752. My minimum sample size, if I use 0.5 as my estimate for p hat, or for the sample proportion. Now with the new graduate suggested 0.3 as p hat. Remember, this ratio squared remains the same, right? No change at that. And then I'm going to multiply that square term by 0.3 times 1 minus 0.3, which is 0.7. I get 631.329, and I round that up to 632. So since the new graduate we only need, or they only need 632 people, and originally the research manager said 652. That's 120 difference, 120 person difference, right? Research manager would have had to interview 120 more people than the new graduate would. So the new graduate saved the firm 120 times $10 per interview, which is $1,200, right? Good. Any questions about that?
No.
No, that wasn't so bad. All right, let's look now at the next problem, which is problem 100. Let's look at the problem itself on the next page. 100, here we go. A consultant conducts a pilot study to estimate a population standard deviation, then determines how large a simple random sample will be necessary to have a given level of confidence that the difference between the sample mean and the population mean will be within the maximum error specified by her client. So they're not even giving you any numbers here. The necessary sample size has been calculated as, what the heck is that? 100, all right? I think it's supposed to be 100. I think that's supposed to be, hold on a minute, let me see what the book says.
Yes, it is 100.
100, yeah, that's some typo here. So n is equal to 100. If the client suddenly decides that the maximum error, and when they say error, they mean what? They're talking about margin of error.
Right.
That the maximum error must be 1/4 that originally specified, what sample size will now be necessary? Now, Steve, I think you already know the answer, right? You're kind of nodding your head. You don't even need to do the calculation. Han, do you know the answer up front without doing anything?
No.
I know Steve knows this because there was something like this in the homework, I believe, from chapter 8.
Yeah,
Yeah.
there was. It was almost identical.
Yeah, you might have, maybe you don't remember it, Han. You did the same problem. It was a problem like this. Well, go ahead, Han. Remember, there's nothing given in this problem except for the sample size. So it's saying, all right, what if the margin of error is now 1/4 of what we originally wanted? Keeping everything else the same, what sample size is now necessary?
Oh, I recall that.
Yes,
That-
yes.
Yeah.
So what is your answer? What do you think the answer would be?
I have to calculate.
All right, go ahead. Now, for the benefit of Rose, I'm going to show the solution on the screen. So, yeah. So, in case she's not, doesn't remember from the homework. I'll give you another minute, hon. I don't want to stay, have you guys on too late tonight. Just one more minute.
Sixteen 16 times.
All right, so what is the answer? You have to give me a number.
Oh. 1,600.
Right. Okay, good. Good. All right, so that's the, I guess, Steve, you got that, correct?
I
Yeah. So the whole idea here is the margin of error formula. Let me get to that. Here. Looks a little different when we are estimating a mean, because the margin of error is the critical value. Now, remember, in this case here, we cannot use a t critical value. We must use a z, because the t is dependent on the sample size. We can't solve for n and know what the t is at the same time, right? Because t depends on that. So we have to have an estimate of the population standard deviation to do this problem, all right? But they didn't tell us what it is. They just said they estimated it. Fine. So the margin of error, I'm going to call this margin of error 1. And N1 is this sample size 1. And notice with this formula here, if I square both sides and rearrange the terms, I have the sample size is equal to this whole thing squared, which is the critical value times the standard deviation divided by the margin of error. The whole thing gets squared, all right? So here's the point. If this is equal to 100, right? This is equal to 100. Now, suppose we have another sample where we have 1/4 of the margin of error. Now, which means that the margin of error for the second sample, that's why I call it ME2, is equal to 1/4 ME1. All right, that makes sense? Now, the sample size, the minimum sample size formula is still the same thing, except for N2, I'm going to replace ME1 with ME2, right? Because now we have margin of error 2 with a sample size 2. The numerator remains the same. There's no difference in the numerator. Now, since ME2, the margin of error for this in the second case is 1/4 the margin of error in the first case, I replace ME2 with 1/4 ME1. Algebra okay so far? Yes?
Mm-hmm.
Yeah. I'm just showing you the algebra so that in case Rose would rather use algebra instead of doing it in her head. Now notice the denominator has a number in it, and it's 1/4 in the denominator. So if you have a fraction in the denominator, you just invert it and move it into the numerator. Remember that from high school. So 1/4 in the denominator is the same thing as multiplying by 4. And 4 squared is what? 16. And what is z times sigma divided by me1 squared? That's 100. That's 100. You just take the 100 and replace this term here, this square term here, with 100. It's equal to 100. 16 times 100 is 1600. Make sense? See how the algebra works? The whole idea is if you change the margin of error, if you make it smaller by a certain multiplier, you have to square the inverse of it, right? Square the inverse of it, and that'll give you the factor that the sample size must be increased by. Okay, makes sense?
Mhm.
Okay, let's look at 104. So hopefully Rose, you understand it. I'm not here, but hopefully you get it. Let's look at problem 104. This will be the last problem and then call it a night. All right. So let's read through it. To gain information about competitors' products, companies sometimes employ reverse engineering, which consists of buying the competitor's product and taking it apart and examining the parts in great detail. Engaging in this practice, a bicycle manufacturer intends to buy 2 or more of a leading competitor's mountain bikes and measure the tensile strength of the crossbar portion of the frame. Past experience has shown these strengths to be approximately normally distributed with a standard deviation of 20 pounds per square inch, PCI. All right. So we have what? We have our standard deviation, which is a population standard deviation, correct? Saying
Yes.
the population is approximately normally distributed and has a standard deviation of 20 pounds per square inch. If the bike purchaser wants to have 90% confidence that the sampling error will be no more than 5 PCIs, how many of the competitors' mountain bikes should be purchased for destructive testing? Minimum sample size problem here. I want you to use the same formula as we saw in the previous problem, problem 100. Use that same formula and come up with the minimum number of bikes that this guy should purchase for this reverse engineering process. He looks like you've already come up with an answer. And Han, are you almost there? You have an answer.
But I got the idea.
Oh, you got the idea. Okay. You got to translate it into a number for me. From idea to creation. So Steve will hold off just for another minute. See if Han can.
Sure, yeah.
I'm okay with seeing the answer directly.
Oh, you want to see it? Okay. So Steve, how many bikes do they have to buy?
I'm not sure about this, but I think it's 44.
44 is correct. So let's look at the solution. And again, we're just using that formula. Now, in this case, the population standard deviation is 20. you want a 90% confidence interval, and the margin of error, you call it sampling error in this case, but it's the same thing. Margin of error is 5. Remember, it's an estimate. We're using the sample to estimate the mean, right? Samples first sample mean. So 90% confidence interval is for, or Z critical value is going to be 1.6449 as I used before. 20 is my standard deviation, population standard deviation, and 5 is our, right? Margin of error is 5, right? We're not dividing by 100, multiplying by 100 here. It's 5, period. 5. So it's 5. And we square this ratio. Square it. You get 43.291 rounded up to 44 bytes. That's the minimum that he needs to look to destroy, I guess, to do the reverse engineering. So he's 90% confident, right? That the true mean, right? That when he does this whole thing, the true mean is going to be in his confidence interval, right? That comes up with, yeah. All right, that's it. So I think what we did in this group of problems is everything that you really need to know to construct confidence intervals, both for a mean and for a proportion. Now the question, of course, would be, what if we had a confidence interval for difference in means and difference in proportions? Suppose we had two groups. I don't know if they have this in this book. Let me see if they do. This strictly deals with one population, not two. There's anything that we need to look at for confidence intervals for this. They do have hypothesis tests for two sample means and proportions. They do mention that, chapter 11. But they don't do it for confidence intervals, but they could. They could do it for confidence intervals. If we were comparing two populations and we were simply subtracting their means, right? We could have a confidence interval that looks at the difference in means and difference in proportions, okay? In other words, the left endpoint would be the difference in means, the right endpoint, difference in proportion, the difference in means or proportions. You get the idea? We're comparing, let's say, instead of saying, looking at one mean, estimating it, we're interested in the difference of means between two groups of people, males and females, for example, or two manufacturers. Maybe they had two manufacturers they were looking at, like in this problem here, all right? So they wanted to look at the difference in the means. So you can estimate differences in means too, or differences in proportions. But that doesn't seem to be something they do in this book, but they will go over it in chapter 11 for hypothesis tests. So just be prepared that we will be looking at sometimes two populations and looking at their differences in means or proportions. All right. And then I guess we have, after that regression, we don't have much time left, right? We just have basically December, whatever's left in December, a couple of weeks in December. So we have to cover hypothesis tests. We have to cover regression. Both those topics will be covered for the rest of the course. So don't worry about it. I know exactly what needs to be covered. So what I'm going to do again, like I mentioned at the beginning of the session, is I'm going to record a video sometime tomorrow, which is an introduction to hypothesis tests, which is the what covered in chapters 10 and 11. All right. And so we'll take about so that way when we get back from our break, Thanksgiving break, we could just jump into how to actually do these things as opposed to the theory behind it. So the theory behind hypothesis tests, which is really the theory behind doing research in general, will be discussed in this video, all right, that I'm going to create. Just the basics, basic idea of it. And then the mechanics of how to do it will be brought to your attention starting next week. All right. There isn't a great deal of time. If we were going to do this in a good way, we would probably want to devote 2 or 3 weeks to just chapters 10 and 11, but we don't have that. We only have about a week, maybe 3 sessions to cover chapter 10, and maybe 2 sessions to cover chapter 11. I have to see how the syllabus looks, and I think we have 1 more week after that for regression. So it's always a bit of a crunch at the end teaching these courses because they don't make them 4 credit. These should be 4 credit courses. They shouldn't be 3 credit courses because there's so much material to be covered. So most students kind of.
It's not?
This is not a 4 credit course, 3 credit course. Isn't it true? 3 credits?
Oh, I don't know.
Yeah, 3 credits because originally it was supposed to be twice a week, 1 hour and 15 minutes each session, right? That was the original time for in class. That was the way it was supposed to be done in class. So that's a 3 credit course. It would have been 1 hour and 45 minutes each session. It was a 4 credit course. So statistics generally, I don't understand why. I mean, they teach calculus 4 credits, right? Calculus is taught as 4 credit courses per semester, but not statistics. And it boggles my mind why not. You know, and the professors who run these departments always say, I don't understand why students don't get it. Well, that's because you rush through everything. It's an obvious answer. I can't say it to them because I don't want to insult them, but it's pretty obvious what the answer is because you're rushing through it. You either make it a 4 credit course or you skip what we're about to cover. We skip it and have a second semester that covers inference. But for some reason, I don't know why, but people are just stuck on that it has to be 3 credits, which means every professor rushes through all of this at the very end. Now, that will start next week. I think it will help doing this video for you guys. For the people at Rowan, it's actually a lower level course than this. It's a statistical literacy course. So they're going to be using StatKey to do hypothesis tests. They're not going to use formulas at all. So I'm going to stop short of actually showing formulas on this video. But having that background of what it is, exactly what it is, really will help you just jump right in next week with how to do these things and how to set it up. It's not that hard, not as hard as it sounds. Most people are okay with it if they really spend a lot of time on it. But I think you guys, knowing you guys, and you're all doing well, shouldn't be a problem. I mean, test number 2, all 3 of you did very well. So good scores. Now I did work on the homework today. It's all updated now in Canvas. So your overall score is correct. It's actually, that is your overall score because I do adjust the tests so that the percentages come out correctly. So what you see as your overall score is the correct score right now. So what are we missing? We're missing maybe 2 more quizzes or something. I'll give you 2 more quizzes. There's probably a couple more homeworks I'm going to give you, project homework type of thing. And then we have a final exam. Now it's going to be a final exam because of the fact that you're remote. If I was going to give a project for this course, I would have had you go out and do an actual survey. But with the second wave of COVID, I don't think that's a good idea. Unless you survey your dogs or something. Which I guess won't work very well. So what we're going to do is do an actual exam. I think it'll work out fine. And, don't worry about it. It'll be reasonable and you should all do very well. All right. So you're all good students, all 3 of you. Any questions about anything? So I'm basically going to let you take a break. There's no homework. You should watch the video before the next class, but you know, you can wait till Sunday or Monday to do that. And but there's no other work for you to do. All right. So Han, are you good? Are you still thinking about the dogs? You're thinking, how does that work? How do we interview the dog? Um, creatively, that's how you interview the dog. I don't mean to discriminate against cats or guinea pigs or any other animals that would not get COVID. But anyway, I'll leave you on that note. It's 10 o'clock right now. So any other questions? Are you all good? Looks like
I'm
Han
good.
is frozen. Han is frozen with her laughing right now. She's completely frozen. But that's good. I'll leave it at that. So I will see you guys. Oh, you stopped smiling. Okay, there you go. You were completely frozen. Your smile there.
Oh my god.
So anyway, that's it for today. I'll stop the recording and have a very nice Thanksgiving.